So as we mentioned earlier, we're going to look at thermochemistry in two different lights. One in respect to physical changes or phase changes, and then later on we'll look at chemical changes. There is an essential topic that we must cover in reference to phase changes, and it has to do with something called an intermolecular force. When we do a phase change, we kind of mentioned earlier that it's a physical change. We're not changing the chemical structure of a particle. We're just changing the arrangement of the particles. So for example, if I do a phase change, I might take H2O in the solid phase, and maybe I turn it into H2O in the liquid phase. That is a physical change. The particles are still the same structure, H2O. I didn't break any bonds or I didn't change it chemically. I just changed the arrangement of the particles. I added energy so that the H2O molecules can move around more and they're not as tightly packed. That's what we're talking about in a physical phase change. In a chemical change, let's put that down, a physical change. In a chemical change, we might take those H2O molecules and, I don't know, maybe they're liquid or solid or gas, and we would chemically split the molecule to form hydrogen and oxygen, which if I want to be crazy and balance it, it would look like this. That is a chemical change. Now they both involve energy changes, and we'll talk about both of them at some point in this unit. But for now, I want to focus on the physical change. So when we do a physical change, we are not breaking bonds. That would be chemical. But what we do need is energy to overcome something called an intermolecular force. Intermolecular forces are the attractive forces between the molecules. Now think of them as molecular glue, attractive forces that hold molecules together. If the intermolecular forces are strong, the particles are more likely to be in the solid phase. The attractive forces between the particles are holding them together very tightly. If the intermolecular forces are weaker, the particles are more likely gases, where the attractive forces between the molecules are weaker. So when we change phase, we're concerned with overcoming intermolecular attractions. So I like this diagram. This is the intermolecular force. It is weaker than a bond. The bonds would be ionic or covalent. The bonds involve transferring or sharing electrons to hold the atoms together and give both atoms a full octet, making them stable. That would be a chemical change. If I were to break this bond, that would be a chemical change. In this case, resulting in like hydrogen and chlorine gases. If I break this attractive force, that's a physical change. A phase change. I'm separating the molecules so that maybe now instead of being in a liquid phase, they're in a gas phase. But I am not chemically changing the structure of the particle. Okay, so intermolecular forces, attractive forces between the molecules. There are 3 different types. And so let's look at these London dispersion forces. London dispersion forces are the weakest intermolecular force. So often, these particles are gases. So some of the examples that they have listed here, neon. I mean, this could be any noble gas, hydrogen, oxygen, nitrogen. Often gases. Or, let's put this down, often gases or non-polar molecules, which they kind of have up in here. Attractive forces between two non-polar molecules or atoms of noble gases, or any gas for that matter. And we kind of mentioned then that these should be weak attractive forces, meaning that the particles are not held together very tightly. Well, let's talk about this then. Obviously in the gas phase, the particles are not attracted to each other. They're real far apart. They have lots of kinetic energy. They bounce all over the place. This could also be the case with a non-polar molecule. And so it could be like H2 hydrogen, where if I go blast from the past and draw some Lewis dot structures, I could connect the dots between the two hydrogen atoms. They each have one valence electron. This would be a non-polar bond, and since it's the only bond in the molecule, it's a non-polar molecule, meaning that the electrons are shared equally between the two hydrogens, and there's really no substantial partial positive or partial negative. So the molecules really aren't that attracted to each other. Same thing might happen with like, well, let's say we have CH4. 2, 3, 4. And remember how we'd have the 4 hydrogens? Like, hello, December. There we go. Something kind of like that. CH4 is methane gas. It's a gas. Which again means the particles are not attracted to each other. Because they're nonpolar molecules, the hydrogen-carbon bond might be a little polar. The electronegativities are a little different. But because those 4 bonds are arranged equally around the central carbon, their little partial poles kind of cancel. And we call this a nonpolar molecule. There's really no region of partial positive or partial negative to attract these methane molecules to each other, meaning that they're most likely in the gas phase. Now let's talk about a temporary attractive force that does result between these particles. Okay, a temporary or momentary dipole. Dipole just refers to areas that are partially positive or partially negative. So we had that like squiggly Greek symbol. That means partial. That'll come up again. Partial positive or partial negative. That's what it means by saying that a particle has a dipole. Let's say we're talking about a particular atom. It could be a noble gas or whatever it might be. Most of the time we think about there being the nucleus, and the electrons are evenly distributed around that nucleus, and they're in their orbitals. But electrons are negative and they're kind of repelled from each other, so most of the time we think of them as being evenly distributed around the nucleus. However, electrons are free to move, and their movement is very random. So let's say that for a split second in time, by random chance, the electrons are not evenly distributed around the nucleus. And so for that moment in time, whoopsie, I didn't mean to do that, we may create an uneven distribution of electrons around the nucleus. And if there is a region that has a greater concentration of electrons are negative, and that would result in a partial negative. The other end of the atom would have the partial positive. It's lacking the electrons, so I just have this positive nucleus. Now this could happen with an atom, it could happen with a molecule. For example, we would think that 99% of the time, the two electrons in this hydrogen-hydrogen bond are right smack in the middle of the two hydrogen nuclei. But again, the electrons are always moving, and their movement is random. So if by random chance, for a moment in time, the electrons were closer to one hydrogen, that could create a partial negative. And then the other side would be partial positive. That's a dipole. Dipole meaning that the particle has a region of partial positive and a region of partial negative. However, when we're talking about these gases or non-polar molecules, this dipole is temporary or momentary because the electrons are moving. They're constantly moving. So this is only for a split second in time, or by random chance the electrons were not equally distributed around the nucleus. I mean, this next second in time, the electrons might be evenly distributed. And then I don't have this partial positive or partial negative. It's a random, temporary, momentary dipole by random movement of the electrons. But now here's what can happen. Let's say for that one split second in time, I do have an unequal distribution of electrons. Well, then this side becomes partially negative. And let's say that happens to another neighboring atom or molecule, and there is a region that's partially positive, because this would represent the positive nucleus. Well, then for that moment in time, there is attraction between a partial positive and a partial negative. This is called the London Dispersion Force. If you want to call it an LD force, I'll totally know what you mean. The LD, London Dispersion Force, is this very weak attractive force that results from a temporary unequal distribution of electrons around a particular atom or within a particular nonpolar molecule. It's very temporary, which is why these attractive forces are really weak. This partial positive, partial negative only lasts for a split second in time, and then it's gone. And then the particles might be back to an equal distribution where there is no partial positive or partial negative. So when I think of London dispersion force, I think of the unequal dispersion of electrons that could temporarily result around a nucleus. And if that happens to particles that are near each other, there could be a very weak attractive force. Now, since this attractive force is weak, I would expect these kind of particles to have pretty low melting or boiling points. It's not going to take a lot of energy to separate these particles because the attractive force is weak to start with, which again is why they are often gases.